Hey physics students, welcome to this screencast by yours truly, Mr. Welch. I had a few people ask for a screencast about torque, so that's what this screencast is going to cover, and mostly it's just going to be a couple problems actually, with more advanced torque problems. So just to start out, I just want us to go over that rule that we came up with on that pink sheet that we did in class. So the rule that we came up with was that torques on one side of a fulcrum or a pivot have to equal the torques on the other side. And we formally said then that torques counterclockwise are equal to torques clockwise. Okay, and you could possibly have more than one torque on a side. So really, we could write this as a summation of torques counterclockwise is equal to a summation of torques clockwise. Okay, so this is kind of like the general equation here, and it can get extended out to this because we could have more than just one torque on each side. We could have two, we could have three, we could have four, so problems can get really complex, but just remember that you can add up the torques on either side of a fulcrum. So here's our first problem. A miserly vendor is trying to make an extra profit by shifting the balance pan of his scale. So like back in the old days, vendors would sell various things. Like, so let's just say that this guy's a fruit vendor. They'd put the fruit on one side of the scale, and then the people would lay coins down on the other side of the scale to balance it out. Well, if you shift the scale a little bit, this vendor is going to end up getting a few extra coins. So that's what's going on in this scenario here. But the scenario is irrelevant. We just want to focus on the physics. So he places a 0.05 kilogram mass on one side of his scale and a 0.049 kilogram mass on the other side. So if the pan with the 0.05 kilogram mass on it is 10 centimeters away from the pivot point, which is right here, where should the other pan be so he can make those few extra coins that he wants to make? So what do we have here? I have all the givens listed. I have my beautiful picture here, which again I encourage you all to draw pictures in these physics problems. It makes life so much simpler, so much easier. But anyway, so mass 1 I have listed for the bigger mass, the 0.05 kilogram mass. Mass 2 is the 0.049 kilogram mass, and distance 1 is here, and that's 10 centimeters. And remember, we have to convert that into meters, so it's 0.1 meters. And our job is to find distance 2, this distance over here, where the 0.049 kilogram mass is. Now we have to remember when we're talking about torques, and we're using torques to calculate these problems, we have to remember that torque is actually equal to a force perpendicular times a distance. Okay, so forces cause torques. Okay, forces perpendicular cause torques. It's not masses that cause the torque or the rotation. It's the force that's, as a result of those masses. Okay, so what we have to do in this problem in reference to that is we have to, calculate what the gravitational force is on these masses. So I'm going to write out what the actual values are. I'm not going to actually show you the calculation because we've done these hundreds of times now in this course. So the force due to gravity on mass 1 is 0.49 newtons. And the force of gravity on mass 2 is 0.48 newtons. So very small differences in forces here. But in the problem, it's going to make a huge difference when we're trying to calculate out this distance 2. Okay, so I'm going to slide down a little bit here, and we're going to actually calculate this problem out. So remember that torques on one side have to equal torques on the other. So we say that torques counterclockwise are equal to torques clockwise. So what do we have on our left side? Well, let's go up and take a look at our picture. We have our distance 2, correct? And we have our mass 2, but we converted our mass and we actually found the force due to gravity on that, okay? So we have F2 and D2 on this left side, and on our right side then we have distance 1, or D1, and we have mass 1 or force 1, okay, which we calculated out. So let's write out these symbols in our equation down here. Okay, so our left side, we said we had F2 D2 is equal to F1 D1. And what was our job in this problem? Well, we had to calculate out D2. So let's just do a little algebra here and rearrange this equation to solve for D2. So we're going to have F1 D1 is divided by F2. And now we're going to just plug and chug here because we have all of these. We have all of these values, and we need to find D2. So we'll just plug in all our values. We said that F1 was 0.49 newtons. D1 was 0.1 meters. And our F2 was 0.48 newtons. And if we calculate that out, our answer for D2 is 0.02 meters. Or we could write this as 10.2 centimeters. Okay? So there's our answer for this problem. Pretty basic. With these problems, just always remember that we need to use this equation. Okay? Torques on one side equal torques on the other. All right, now here's a problem that's a little more complex than the last one that we did. We have a 2.8 meter long beam in equilibrium. So in equilibrium, sides are balanced, right? Torques are balanced, torques are equal. And this beam has a weight of 355 newtons, and it's suspended from a point that's 1.5 meters from the left end, okay? So that's this distance here. Susie, who weighs 500 newtons, is standing at a point 0.4 meters from the left end. So our job is to find out how much Jimmy weighs over here if he's standing 2.4 meters from this left side. Okay, so again, just like in the last problem, I drew a nice picture. I have my givens listed here. I want to go through these givens. Okay, so here I have force of Susie, okay, her weight, 500 newtons. I have her distance from our fulcrum, right? Our fulcrum here is where that beam is being suspended from. Okay, and her distance from that would be this 1.5 meters minus this 0.4 meters. So our distance is 1.1 meters. I have this FB, this force B, and this is the force of gravity on the beam. And where is that force actually being applied? Well, it's at our center of mass of the beam. Okay, we started talking about center of mass in class on Thursday. So our center of mass for this beam is right smack dab in the middle. Okay, this distance here is half of the length of the beam. So our distance that this force is being applied from our fulcrum is just going to be this 1.5 minus half the length of the beam. So we actually get a distance of 0.1 meters for that. And our job is to find how much Jimmy weighs. So that's a question mark. But we know that Jimmy is a distance of 0.9 meters from the fulcrum, okay, because he's at 2.4 meters. The fulcrum is at 1.5. Subtract that out, and we get that Jimmy is 0.9 meters away. All right, so remember our golden rule with torques. What do we say? We say torques counterclockwise have to equal torques clockwise. Okay, so what do we have on our left side that we have to focus on? Our counterclockwise torques. Well, we have to focus on Susie, and we have to focus on our force due to gravity at our center of mass. Okay, on our right side, all we have to worry about is Jimmy, and our right side is going to give us what his weight or his force due to gravity actually is. So let's plug in this known information that we have here. So we have Fs, or force of Susie, times distance of Susie, plus force of the beam, distance of the beam. That's our left side. Those are the torques counterclockwise. And this is all going to equal force of Jimmy times the distance of Jimmy. Okay, so these are our torques counterclockwise. These are our torques clockwise. Now, our job, remember, is to find our force due to Jimmy. So I'm going to actually do the algebra here to get force of Jimmy all by itself. Okay, so this is going to look like this. Force of Jimmy is going to be all of the left side. Oops, got a little ahead of myself there. Okay, everything on the left side from our previous equation, but it's just going to be divided by the distance of Jimmy. Okay, the distance of Jimmy away from that fulcrum, or where the beam is suspended. And now from here, again, it's just a plug and chug problem. We just plug in all of our known values. So what do we have for our force of Susie? We have 500 newtons times 1.1 meters. And this is going to get added to the force of the beam, which was 355 newtons. And this is going to be times by the 0.1 meters that the center of mass is away from the fulcrum. And this is all going to be divided by the distance Jimmy's away from the fulcrum, which is 0.9 meters. And that's going to be all equal to force of Jimmy. So if we calculate this out, we get a force of Jimmy, the gravitational force of Jimmy, or his weight, is equal to 650.6 newtons. Okay, so these are a little more complicated. This was a complicated problem, right? Pretty long multi-step problem where we had to look at a lot of things to get our given information. Okay, we had to kind of break down this scenario and get all these values. The real takeaway, though, is from both of these problems that this equation is king. Okay, torques counterclockwise equal torques clockwise. And then you can just set up everything that you have on one side is equal to everything you have on the right side. And it makes problem solving very easy for these torque problems. All right, so there's your screencast on torque, physics students. Have a good weekend. We'll see you on Monday.